So my name is Christopher Nuland. I'm a technical marketing manager at Red Hat, focusing in AI. A couple interesting stories that relate to this. First, my degree was originally in AI. I went to Purdue University, if anyone's familiar with it. And I was focusing on AI at the time. And my junior year, my advisor told me that AI wasn't going to go anywhere. And I needed to figure something else out unless I was going to get a PhD. And so I switched doing more distributed systems and container work and systems. And then when everything kind of happened with AI a few years ago, I refocused back to doing a lot of stuff I was initially interested in, and kind of combining that with the work I've been doing here at Red Hat. So second thing is the project that I'm going to be sharing with you today is the reason why I have the job that I have now. I was, 2 years ago when we were forming a technical marketing team around AI, I was working on this project for fun. It was just a fun project I was working on in the evenings. And I was asked if I could interview for this position, and I went for it. And then I had a presentation built, and I had this whole other project planned. And one of our vice presidents was on the panel, and he's like, hey, I was actually stalking your GitHub page. You're going to talk about this Double Dragon project, not this other project. So on the spot, he's like, you're going to do this. And he loved it, and everyone loved it, and this is actually the reason why I have the current position that I have. So it's gone through a few iterations. I'm showing you the latest iteration. But first, I kind of want to give you an idea of what we're working towards. So what I'm about to show you is actually the final playthrough. This is the AI model that I built to beat the game, which I'll show you how I built it, the different technologies. This is the actual final playthrough. So this is the first level. As mentioned before, eventually, the AI learned that punching from behind, so using its elbow, was the most effective way to go through the level. It goes through very quickly by finding a corner and then letting NPCs come to it with his elbow move. Eventually, he'll make his way into the boss battle, where he'll do this very same move, but make sure to position himself in the corner. And you can see here, he finally beats the boss and moves on to the next mission. So that took way more compute power than I would want to admit. So if you want to know where all your GPUs were going, let's go into this. One cool thing is I showed this video to a speedrunner that actually does speedruns of this game. And he was fascinated because it was some of the same techniques actually that they use in speedruns for this particular game. And he's like, it was really fascinating to see that the AI had actually developed this kind of some of the same techniques that some of the people who are more involved in that gaming community. So if you're not familiar with OpenShift, I'm going to show you a couple OpenShift views. So when I'm doing training for this, each of this training is happening in a KubeRay cluster. So Ray is a popular tool for distributing different AI libraries across different types of systems. In this case, I have quite a few. This server, I have someone bugging me every morning saying, why are you spending so much money? But this is I'm spending so much money cluster on video games. I'm also doing some other stuff on here, but this is split between 24 A100s right now, because I'm experimenting on a couple things. This is more to kind of prove a point, but I'm using those A100s for other things, not just video games. So there's a lot of compute right now. I actually have enough here where I can run about 100 sessions of the emulator pretty easily. I'm actually not capped by memory or anything. I'm actually capped by more storage capacity right now within my cluster, because I save this, which you'll see here in a moment. But these are all the sessions, all the instances of the emulator that is running. Now, on that note, I gave this same presentation a few months ago. And anything that we present gets sent to Red Hat Legal. And I had an email from Red Hat Legal a few weeks before this event. Never a good sign. Like legal is never usually reaching out to you for good reasons. And so they're like, hey, we know you're doing this presentation. We just need to make sure, do you actually own this game? I'm here to tell you I own multiple versions of this game. When you see this running, it is actually my version of the game that I have copied over. And Red Hat Legal would like you to know that before anyone gets any ideas of suing us. Anyway, so we've got each of these instances are on their own machines, and each of them can run upwards of about 15 versions of the emulator running. There's a lot of ways that I could tweak this to actually even have more instances, but I find when I go over 100 instances, I actually start losing some value in the training runs. So, but just to show you the amount of compute when we're talking about this. And I'm sitting here talking about video games, but the same kinds of methods are used in robotics, they're used in healthcare and weather, all kinds of critical areas in science and industry. So this is just a fun way of showing you some of the cool tools that we have that can be applied in many of those industries. This is what the cluster actually looks like too. These workers are the ones that I have assigned to running the game. So the control plane masters are the ones that are actually running Kubernetes. And then these workers are the ones that I actually have compute assigned to actually run it. So I just wanted to kind of give you an idea of what the footprint looks here. I've got 3 servers running each of them have 8 A100s dedicated to them. And if you're not familiar, that's an NVIDIA. I think one of those is going for maybe like 20, 30K a pop right now. So they're not the top of the line, but they're right under that. They're pretty valuable when we talk about. I'm going to come back to that. So here I have OpenShift AI. So OpenShift AI is a tool set within OpenShift that allows you to run different large language models. You probably have heard some of the things that we've been talking about today about VLLM, LLMD, you may have heard the keynote. All of those are components within our OpenShift AI platform. So what I'm showing you here is actually more the data science side. So we can create these data science projects that allows us to run these types of experiments, all within this nice UI here where you can kind of switch between your different projects. You can collaborate with people. In my case, I'm going to be using it to coordinate actually launching this machine learning process for learning how to play the game. But I have this workbench here, which is a notebook that I can go into and show you a little bit more about the experiments that I have here. We also have the ability to do different types of metrics off of that. I can save different types of experimentation or feature engineering aspects of my experiments. I can manage for like LLMD and VLLM that you learned about earlier today. That can all be also managed from this dashboard. So if any of you are students in machine learning or computer science, or if you're in the industry, this probably looks very familiar. This is a Jupyter notebook. For those of you who are not in this area, just think of this as an online IDE that is more specific to running experimentation for data scientists, statisticians, mathematicians. It's not usually used to build large applications. It's more about getting visual representation of data and experiments that are running within a cluster like this. So I'm using a few different tool sets for this right now. So Codeflare is a wrapper for Kubeflow. And it also, Kubeflow and primarily KubeRay. So it's doing all the orchestration of the experiments. So it's basically scheduling to the Kubernetes operator that we need these instances up. And it also helps with the orchestration of the Ray instances that will then manage those. So Ray is probably the most important thing here. So Ray is very, very popular in the data science community. It's heavily used in high-performance computing, in different areas of simulation, and in AI. And it's what does the coordination. It's what assigns the algorithm and then sends everything out to be split up amongst the different nodes. And then it's also what's in charge of bringing everything back each iteration to kind of compile over that. And that's how I'm able to get 1,000 instances of the game or 100 instances of the game out and training all at once. So I'll walk you through what a typical experiment looks like. I log into the cluster using this so that it knows where to deploy the experimentations. And then here is where I set how large I want each node to be. The head is just the coordinator. It's the one that is actually orchestrating all of the different workers. So there's only one of those, if you saw in the previous view. But then the workers are the ones that you saw that are actually being assigned to a GPU instance. And as you see, we can specify different CPUs. We can specify memory. We can also specify even GPU requirements here. I'm letting it have free form over all of its GPUs because I don't want to mess with that. But you could even limit some of the aspects of what type of GPU compute you're using here, which makes it a very, very powerful tool when we talk about data science. I have an image as well. So this image was the biggest paying of this project. I spent a long time on this. So this image is what runs the emulator. So I have an instance of the emulator, PyBoy, running. I got started in programming by hacking Game Boy games and Super Nintendo games on emulators back in like the late 90s, early aughts. So this was a fun project for me because I got to kind of revisit where I started. And all of the information is actually coming straight from the memory from the emulator. I'm not doing any type of image recognition here. All of it's getting pulled directly. Even the screen itself, I'm pulling the pixel map from the Game Boy emulator and directly applying that into the matrix that was working with this particular machine learning algorithm. I'm going to go through this quickly because we have a pretty limited amount of time. I already have a cluster up. I want to see if this kicks off. I was having some issues with the internet earlier. Yeah. So I already have a couple instances running, and I'll kind of show you what that looks like. In Ray, these have all failed, not because of any technical issue. They're failing because they're not giving me the results that I'm wanting. What I'm trying to do right now is to beat the second level. And the way I'm actually doing that, if you're curious, for those of you who are familiar with machine learning, there's this concept of overfitting. So what happens is that the AI has basically learned everything about the first level, and it thinks it knows everything. But then when it gets to the second level, things have changed. Does anyone know what changes between the first and second level of this game? I'm curious. Is there anyone in the audience that might know? Yeah, yeah. There's new enemies that have new characteristics. And also, the biggest thing is the first level is on the x-axis. The second level goes on the y-axis because you climb up the stairs as like these little ninjas are flying off the screen, jumping off of like helicopters and stuff. Yeah, so this is actually just a really interesting aspect of it. So the way I'm actually doing this is I'm training it over different saves over the entire game randomly so that it doesn't overfit on the first level with hopes that I get further along. But I can kind of show you, I'm not going to sit on this too much. The critical thing here at the end, let me see if I can find it, is this final state line right here. And this gives me an idea of, for this instance, how much it scored, how far it got. Levels completed is actually the most important thing for me. Like this instance, I can tell you it probably just got stuck in a corner and didn't do anything. Doesn't have very much score. It didn't progress very far, and it has all of its lives left. So the emulator actually timed out rather than doing anything, and that's very common for a reinforcement learning algorithm like this. Of the information I have here, any guesses of what's the most important? what do you think actually is kind of the best bang for your buck? So you've got lives, you've got score, and you have levels completed or distance traveled is what I would describe it. Curious. Anyone right there? It is. It's absolutely distance traveled. So this is not just a double dragon thing. This happens throughout all areas of reinforcement learning. It has applications in robotics, in protein structures, everything. What we find is that discovery and exploration is actually what gives the best results. Because what happens when you do score is that very often the game will just start gamifying it, where if I overvalue score, what it will do is it will go as far as it can in the level, get as many points, and then it's going to jump off a ledge, kill itself, go back and repeat the whole levels again to get the maximum amount of score that it can get without beating the game. There's a group that does this with Pokemon, where they find also that what is the most important metric is the distance traveled. And actually, what's the most important with Pokemon is different distances traveled. So being able to explore new places. So the team that actually has beaten Pokemon Blue using the same algorithm I'm using, they keep a memory map of every place that they've traveled. They keep a cache of it, and they give reward for new things that they have not seen before. And this drives a lot of positive feedback. So there's a lot of, even though this is a game, the concepts in here actually apply to, like I said, robotics, protein structures, a lot of different areas where this is being used. I love KubeRay, by the way. When I first started this project, I was doing it all in the CLI on one server. And now I have this nice thing where I can search and see different values. I also save each instance. So I can show you here, if I come here and click this, this is a Minio S3 bucket on the same server. I actually have an instance, and this is probably one of those instances where he's just getting stuck in the corner. I can give you a better look of what that looks like. This is another one. And I have all this saved. So each iteration actually saves, so I can actually go and see what has actually happened in the emulator to decide how I want to adjust the reward systems in the game. And then I think this one is one where, yeah, so he actually runs into some people. He triggers something here, and you'll see he'll actually start fighting some of these guys. That's a pretty good job. But he doesn't know how to enter that room, which is his main problem right now. And he jumps in this hole every once in a while, which isn't doing him any good. So what this can look like when it's all put together. How am I doing on time in the back? I'll check in a moment. What this whole training cycle looks like, if we put it all together, I can kind of give you an example here. This is a really cool graphic that my team put together for me and has lost the game. Let's go ahead and take a closer look at a training run. This is a video of me going from the 10 instances up to over 100. We have a few things that we'll take note on. First off, you'll see that most of the frames have certain trends that are happening. The majority of the time, we'll see maybe 80 or 90% of the instances following a very similar path. But let's go ahead and look at some outliers. First, we see here that the playing character is eventually getting stuck here. This is preventing it from moving further on in the game. We need to find ways to penalize the model in this case and say getting stuck is a bad scenario. We can do this in a few ways, and I'll show some of those here shortly. Now, let's move to another section where the playing character is actually progressing very quickly through. And you actually saw that one. But I wanted to show you that montage of like what it looks like when it's all kind of going together in a single training run. It's really cool because I can kind of focus on some certain trends that we see kind of form in this. From a project standpoint, I want to show you some details before we end on really what this project looks like. I have you saw the notebook that I was using, the Jupyter notebook. I have some Python code as well that I use for this. So this is the notebook. But if we go and look at the runner is what sets up the Ray instance and the S3 buckets. This is where I specify what save files I want to use, and I let it know kind of where the emulator is. So all of the configuration that's used is managed in this single space. This then all gets applied as environment variables to each worker, but then become available to the emulator to use directly. And then here we actually start setting up the actual Ray instances. What I really want to focus on is some things here. I'm using a CNN-based neural network. This one is moderately popular. I like to use it because it's pretty straightforward. So if you're into machine learning, you're probably familiar with this one. I find the best results when combining this with PPO, especially when we're doing like video games like this. I'm starting to explore some more deep learning techniques with even potentially JRPO. So that's the same reinforcement algorithm that actually was used to post-train like DeepSeek R1, for example. So when you're hearing about reinforcement learning, this is reinforcement learning to me. This is my world. Reinforcement learning, what's in the news right now, is all about how reinforcement learning is being used with large language models like OpenAI's GPT and what we have with DeepSeek R1, for example, that really kind of revolutionized this concept. I should be able to take some of those same approaches and actually apply it to these video games and actually see some even further results. But a lot of that's still new. Some of this is just coming out in the open source community right now. So anyway, I wanted to show that though, because I think that is a kind of a cool aspect. I'm using what's called the PPO configuration. This is a really popular one in the field of reinforcement learning. It's my favorite. Another one you may have heard of is DQN. What I like about the PPO algorithm specifically is it's completely rewards based. It doesn't save any information between each training run. So DQN will actually store more metadata between each iteration. This is just straight up into the model where it's completely rewards based. It just learns off of the feedback from the reward system. And I think for a game like Double Dragon is where I've gotten the best results on. But just know that there's a lot of different tools that you can apply into these scenarios. All this stuff is just high-level machine learning using different lambda and gamma and entropy configurations. But this basically tells it how aggressively it should learn, how often it should try something new versus kind of get stuck in its ways. These are the parameters that I change the most to try to get different types of results out of the model for each training iteration. The most important thing here, though, is this DDM. This is the PyBoy iteration. It actually is what launches the emulator. So a couple of things that are of interest here. I just want to skip to this right here is the action space. This is what tells the algorithm what it can basically button mash to start learning. So here I've got up, down, left, right, A, B. I've got a couple of custom actions here that are titled 97, 98, 99. This is like jump kick and jump punch. So if you guys are familiar with the arcade game, if you did some button combinations, it would do something. Those are just represented as integers here because they're not actually mapped directly to the PyBoy. But this gives you an idea. And never let your PyBoy have the start feature unless you're doing something like Pokemon, because it will just turn itself off sometimes. It will just be like, I don't know. I think the best solution is to just kill it. Was that 10? Okay, cool. And I have seen that before. if you have the start, it will just start button mashing into the menu and just be like, I'll just stop the game. That seems like the best thing for me. So you have to be kind of careful what controls. Sometimes I'll even remove the kick to try to encourage it to get to that point where it's punching a little bit more, because I know that's optimal for performance. So there's different ways that you can penalize that too. For those of you who are in machine learning, this is the observation space. This is where I set up the actual matrix multiplication and aspects of the actual algorithm as well. So that's very high level. It gets into the different shapes that are given by like PyNum and some of the other machine learning. Each tick, what we call a tick, is basically one action, each tick of the Game Boy, and each tick will have a new action associated to it. I can extend that tick out if I want to slow the game down, which might be good for a game like Pokemon, but for Double Dragon, it's about you want it as fast as possible. You want the actions to happen as quickly as possible. Some other cool areas here that I want to show was when I was talking about the memory, and I want to show you how I actually access that. That's all done here. So I used a couple of tools that evaluate the memory. There was actually nothing on the internet. I was very surprised. There was nothing on the internet about where these memory addresses were located, which was challenging. So like I said, I had to kind of relearn some of the things that got me started in this path in my life. And so like an example would be, I would walk up to an enemy, and right before it hit me in the face, I take a snapshot of the memory. I'll let it hit me in the face, I take another snapshot, and then you do a difference between the two. And you see that there's 10 memory addresses that changed, and then you go into your memory modifier and you start changing those addresses to see what happens. Sometimes it'll just flat out crash the game. Sometimes you'll see that your level will go up 1 or 2, I mean, your health will go up 1 or 2. And that's the information that's important to me, because I know that I found the memory address that I needed to pull back down to actually make decisions in the game. And if I'm starting to get older, does anyone remember like the Game Shark? Okay, good. There's some people either my age or older. Yeah, so the Game Shark did that. This is the exact same thing it did. You would go on and you would go on the message boards and find out these individual codes that you put in, and you would change values. Is doing the exact same thing I'm doing here. You just directly access the memory of the game, modify it, and that's how you get extra lives. You would unlock things that you otherwise weren't supposed to see in a game. And I'm just doing that in the emulator to make sure that the algorithm knows what's happening in the game. Because this is orders of magnitude faster than me taking a snapshot every second, which would be very slow response. It takes a lot more computational power. In this case, I'm just scraping memory right off of the Game Boy. This is how I calculate things like where in the level it is, what's going on, is it a boss level? I give it rewards. This is like the reward magnitude. These 15, 84, 48, for some reason, they're the values that are plugged in into the actual Game Boy. I found a spot that represented the level. So some old developer documentation in Japan has these numbers somewhere, associated with these levels. But I use it to award my AI for going further into the level. I have to give it rewards for also X and Y, because I want it to continue moving in the game. If I don't do this, then it's just going to sit in the corner, not do anything. And that's actually what this is doing here. I have to calculate the difference between the X-axis, but I also have to do it for the Y-axis, because there's multiple levels that take place on ladders that you have to climb up go through. So that's my project. I do have, I'm not one for slides very often. I just like, for me, it's like popping up my laptop in a corner somewhere and be like, hey, come check out my cool project. So I'm really excited to have you here because this is something I'm very passionate about. One area that I'm exploring is how to start doing like more speed runs around AI, like posting different models and saying my model either beat the game or it got through this level, it got this far, it did it in this time. So I've been working with a few people in the reinforcement community actually kind of building some of the blocks of what this type of community might look like. So if you're interested, I do have all this code on GitHub. You are more than welcome to take a quick picture if you'd like. You know my name here. That's C. Nuland on GitHub, and it's my Hello Chris DD KubeRay project. It talks about how you can get started running this. I do have some examples of how to run it locally as well, not just on a distributed platform, because that's where I literally normally will iterate off of it first locally before kind of moving it into a distributed thing. So anyway, yeah, definitely. Let me even zoom in for a little bit. And yeah, feel free to take a picture. One thing I want to note is that there is a Pokemon community where a lot of my ideas came out of. I do want to call that out. I don't have it listed here, but if you just search on even YouTube, Pokemon Blue AI plays Pokemon Blue, that video that has a few million views is part of the same community that I'm part of. So I just want to give a shout out to all the people in that community who are very passionate about these types of projects. With that, does anyone have any questions? Here? Sure.
So I know, like, I can send a picture to ChatGPT. ChatGPT will tell me to send a picture.
Mm-hmm.
So I'm imagining that you're sending pictures to something like an LLM, and it's interpreting those pictures, but its output is in terms of those video game. I'm going to move up, I'm going to move down, I'm going to press the button.
Yep.
Let go of the button. And how much memory? Like, does it review the whole game from the beginning? Is it stateless? Does it just like look at, well, this is what's on the screen. My character's in the middle of the air flying.
Yep. That's the difference between DQN and PPO. So PPO, which I'm using here, is basically a stateless version. It is button mashing for all better purposes. It's randomly pressing buttons, and then as it gets reward, but it is so the stream of pixels come in. So whatever's on the screen, so your 128 by 128 matrix gets sent into the machine learning algorithm, so to speak. And it will then button mash based off of what it sees. And there's a neural network there that first starts out random. There's a reward system, and I can tweak that reward system based off of how far it gets, if it beats the boss battle, how much score it gets, how many lives it has. And based off of that reward, it then adjusts the neural network, and all the actions go through the neural network. And then that button mashing turns into something that's not button mashing anymore. It's actually playing a game because it's learned based off of the rewards what it needs to do. And now the Pokemon group, they do use stateful because you have to use stateful because it's a game that has backtracking into it. You have to have memory of where you've been to be able to go back somewhere. In this game is completely stateless. Other question? Here? I run it off of, so the question was, can you run this on consumer hardware? I run this on my Mac, my wife's Mac Air all the time. The issue there becomes it just takes longer. And you can't do as much of the fancy stuff. Like I'm overkill here because this is the cluster I had available because I'm doing an LLMD project with the keynote here. And I'm like, well, I have this cluster up. It'd be kind of fun to attach, like you said, a $250,000 of GPUs to a video game. Other questions? Oh, by the way, this runs on CPU. Actually, what we actually find out, I'm running on GPU now because there is a point GPU is better, but for the majority of GPU, we actually find that running it on CPU cores is faster because it has to do with the emulator. The emulator becomes the bottleneck, and the emulator actually runs better on CPU just because it's older than dirt and it's being emulated as a Game Boy. So just keep that in mind that this is one of those weird cases where CPU may actually be more optimal. I'm doing GPU because I have some experiments here where I'm trying to add some things that will perform better with GPU, but the base project actually runs better on CPU. Other questions? I know we're running out of time. One more, right here.
Yeah, I have a couple, but I guess I'll limit it to one or two. Is there any particular reason you're using PyBoy instead of something like GymRetro?
I'm using PyBoy because it has the easiest API for me to integrate in with what I'm doing with Ray. But to answer your question, it would be more optimal for me to use another emulator because PyBoy is actually really, really slow. But another issue is that PyBoy has really nice API commands when I want to look for memory. And other emulators, it's a little harder to get in there and get the memory addresses that I need.
Have you there's a project that came out very recently that I was thinking of contributing to. It's called PyRetro. It's basically like taking RetroArch cores and trying to give a Python API to it. Have you looked into that?
The person one of the founders of this PyBoy project was one of the people that's working on that one.
Okay.
So I'm familiar with it. I'm really excited about it. I'm definitely looking at it for opportunities. What I really want to do is start doing some Super Nintendo games. I'd like to actually start doing more with like RPG, really like old school RPG games, and see more stateful learning of like the memory, like being able to backtrack and do other things.